Today we're going to talk about how to find the derivatives of logarithmic functions. So we're going to find the derivative of the natural log of x first. And obviously we don't have a rule for this yet. And so we might be tempted to try and write this out as a limit of a difference quotient. But we're actually going to come up with a kind of cool little trick here. We're actually going to just say, let's let y equal the natural log of x. And then let's convert this into a different form that we do know how to take the derivative of. So what we're going to do is what's called exponentiating both sides. Means we're going to raise both sides so that they are the power for e, which gives us e to the y is just equal to x, because we know that e to the natural log of x is equal to x. And now that it's written in this form, there's nothing in here that we don't know how to take the derivative of. So we'll just take those derivatives with respect to x on both sides. And so when we take the derivative of e to the y with respect to x, we end up with e to the y dy dx, because this is done implicitly. And the derivative with respect to x of x is just 1. So we end up with dy dx is equal to 1 over e to the y, when we started off with the function y equals ln of x. Well, we know that e to the y is equal to x. So we'll just say that this is equal to 1 over x. And that's our derivative of natural log of x. The derivative of natural log x is just 1 over x. And of course, we can take that and apply the chain rule with it. We can say that the derivative of the natural log of a function, the natural log of u, is just 1 over that function, and then times du dx, right? This is our dy du times du dx for the chain rule. So if we wanted to find the derivative of the natural log of 3x squared, we could treat this as y equals the natural log of u, where u is just 3x squared. So we would get dy du, which would be 1 over u. So we would get our dy dx is 1 over 3x squared. And then we would just multiply that by du dx, which is 6x, the derivative of 3x squared, which just ends up giving us 2 over x. Interestingly enough, we could actually have done this a different way. We could have just rewritten natural log of 3x squared into each of its component parts. We could have called it natural log of 3 plus natural log of x plus natural log of x, which would have given us, if we were to take the derivative of that, just 1 over x plus 1 over x, because natural log of 3 is just a constant. So when we take its derivative, we get 0. The derivative of each ln of x is just 1 over x. If we want to take the derivative of the natural log of 5 cosine of 2x, we'll just treat this like natural log of u. So our derivative will be 1 over u times the derivative of u, and the derivative of 5 cosine 2x ought to have 5. And the derivative of cosine 2x requires us to use the chain rule, right? Cosine 2x is cosine of u, where u is equal to 2x. So the derivative of cosine u is negative sine u, or negative sine 2x. And then we'll multiply by the derivative of u, which is just 2. So we end up with 5s that cancel, but we still have a negative 2. And then sine 2x over cosine 2x would be tangent 2x. So negative 2 tangent 2x would be the derivative of the natural log of 5 cosine 2x. And that's about all there is for derivatives of the natural log. So it is possible, though, for us to be presented with a problem where we're having a logarithm in a different base. And so there are a couple of different ways we can prove this formula. The easier one here is probably the change of base formula, which hopefully you're familiar with, that log base A of B can be converted into natural log B over natural log A. Or in fact, log base any base of B and log any base of A. It could be log 10 of B and log 10 of A in the denominator. It could be log base 7 of B over log base 7 of A. It doesn't really matter. But we happen to use natural log, one, because it's more convenient, and two, because we know how to take its derivative. So if we were to use the change of base formula here, that would just give us natural log of x over natural log of a. Well, if we want the derivative of that, we have to think about what natural log of a is. Natural log of a is just a constant. So really what this is telling me is, what is the derivative of natural log of x times some constant? Well, that would be the derivative of natural log x is 1 over x. So this just ends up being 1 over x ln of a. And that is going to be our rule for how we find a derivative of log base a of x. But let's go through real quickly and see if we can do this using implicit differentiation as well. We could rewrite this as y is equal to log base a of x, which we know, based on what we've learned from previous classes, means that x is equal to a to the power of y. And if we have x is equal to a to the power of y, we should be able to take the derivative of both sides of this implicitly, giving us 1 is equal to a to the y natural log of a. And when we take the derivative of that a to the y piece, we have to remember that we're going to multiply this by dy dx, because we're taking the derivative with respect to x of a term that has a y. So now all we got to do is solve for dy dx. dy dx is equal to 1 over a to the y natural log a. And as we saw just a second ago, a to the y is equal to x. So this is equal to 1 over x natural log of a. And that's our derivative for log base a of x, 1 over x ln. So we'll do one problem here, and that's really going to be it for these, because these are pretty straightforward. It's just using the formula and implementing the chain rule with it. So the chain rule says it should just be 1 over the function times the natural log of a multiplied by the function. So this is log base 3 of u, which should become 1 over u times the natural log of 3 times the derivative of x to the 5th. And we should be able to simplify that down into 5 over x ln 3. That's really all there is to taking the derivatives of logarithmic functions. Right? You know the two rules, and you apply the chain rule to them, and it's really not much we've added today, just those two new rules that you're going to need to memorize. So next time we're going to use some of these rules for taking derivatives with logarithms to learn a new method for differentiating some functions called logarithmic differentiation, which is a bit different than what we're doing here. So we'll take a look at that next time. That's it for now.